My name is indeed Antoine Murat, and today I'm going to talk about UKharon, a membership service for microsecond applications. So this is joint work with Rachid and Athanasios from EPFL, as well as Huabing and Pengfei and Javier from Huawei. So let's start this talk with an overview of what data centers can look like today. Well, given that modern applications tend to follow a microservices-oriented architecture, well, that data center is pretty much a zoo with many microservices all connected together in many intricate ways. And that's great, because at the end of the day, you get like elasticity. But the problem with this architecture is that when you have a failure, like the one here on top, well, it actually propagates to many microservices and potentially many applications. And so that's the reason why today, maybe more than ever, failures truly are first-class citizens that you should try to deal with as fast as possible before they propagate too much. But like, failures are not a new thing, so how do we usually deal with them? And the answer is that this is pretty much the reason why almost every system, distributed system, uses a service such as etcd or Xygkis. These tools can do many things, but what we're interested in today is their ability as membership services. So membership services, quickly, basically they act as reliable configuration stores. So by configuration, I pretty much mean like what is the set of nodes that are within the system. And it's very important that this configuration or view or membership, they are pretty much the same, are stored in a reliable fashion, because everything in the system depends on having access to this configuration. So you don't want to lose configurations. The second thing is that membership services, they're able to update this configuration in a sequential manner, like by producing a sequence of configurations. And again, that's very important because you don't want parts of your systems to be evolving in different ways. So yeah, that's why we build a sequence of configurations. And lastly, they should be able to invalidate old memberships. To see why the last point is important, we'll go with a small example. So let's say that within our system, we have a data store that is hidden behind a cache. And we have a client that wants to retrieve the value stored in our system. So the thing it does is that it's going to wait for membership. And this membership that it gets, M1 there, is that the cache, C1, is part of the system. So it can use it to actually retrieve the data. The problem is that what it doesn't know is that this cache has long been replaced in a second membership by C2. And so actually, the data it was retrieving from C1 was stale. And that's the reason why it's very important that old memberships get invalidated, so that you don't have parts of your system evolving in a previous configuration. And the thing is that all these features, they're provided by systems such as etcd and Xygkis. But the problem is that they do not evolve at a microsecond scale. So we end up having applications like in high-frequency trading that operate at microsecond scale, but whenever there's a reconfiguration or failure, actually it suffers from like huge latency spikes. And that's a huge deal. And so that's where we intervene with our contribution, that is UKharon. So UKharon is a membership service that operates at a microsecond scale. It's able to detect failures in as little as 15 micros, to update the membership in 10, and then to invalidate all memberships in 25. And so all in all, this allows UKharon to react to failures in 50 micros, and it does so by leveraging RDMA. Because RDMA is pretty much at the core of UKharon, let me give you a short overview of what it is. Well, RDMA stands for Remote Direct Memory Access. It's a networking technology that allows a process to access the memory of a remote one without invoking the CPU of the latter. So in that example, we have a writer on the left that wants to put a message in the memory of the guy on the right. So the only thing it has to do is to send a small request to its local RDMA NIC that is going to fetch data in the local memory and send it over the fabric and install it in the remote memory. And the great thing with RDMA is that you do not invoke the CPU of the machine on the right. And that allows for microsecond-scale communication and great tail latency. So now that we have an overview of RDMA, we can go back to UKharon itself. So the first task that UKharon has to do is to detect failures very fast. And usually in distributed systems, detecting failures fast is kind of problematic because we detect failures by relying on timeouts. And so when you have timeouts, you have two strategies. Either you go with like very large timeouts, in which case you don't have a lot of false positives, but it takes forever to detect a failure, or you go with short timeouts, in which case you're able to detect failures super fast, but you will have a lot of false positives. And that's a problem because you don't want to suffer from reconfiguration that are useless for your system. So timeouts do not help, and uKharon works around this issue by recognizing that not all failures are equal. Actually, there are like many kinds of failures, and for many of them, you don't need to rely on timeouts. For instance, when you have process failures, you can rely on the kernel to get some help and to avoid timeouts. When you have kernel failures, well, you can get help from the RDMA NIC, and again, not use timeouts. Sure, when you cannot communicate with the machine at all, for instance, there's a power failure, then you have to rely on timeouts, but hopefully, because the fabric is fast enough, you can tune the timeouts that you're going to be using for RDMA. There's a kind of failures that we don't deal with, and those are Byzantine failures. They fall out of our scope. So let's have a quick look at how we deal with the first two kinds of failures. Well, when there's a process failure, it's dead simple. The app just pre-registers itself to the kernel and tells it, please, when I crash, send my ID over the network, send a crash notification. And so when it happens, the kernel is going to handle the death of the process and simply send notification over the network. This is dead simple, this does not involve timeouts, and this is 100% accurate. But sometimes we cannot even get help from the kernel. For instance, maybe the CPU is hanging, so that's an issue. And that's why we use another failure detector that we run in parallel. You see, for that failure detector to work, what we mandate from the app is to have a counter, local one, that it exposes over RDMA. And it's going to increment that counter in a timely manner. Then, as a remote node, what you do to detect a failure of this app is that you're going to read that counter over RDMA. And if by reading twice in a row you detect that this counter has not been updated, then you know that the app has crashed. The very neat thing with that failure detector is that it works even if the kernel is dead, even if the app is dead, because RDMA truly does not need the CPU to be working to access the memory. So the only thing that you need for that failure detection mechanism to work is that the RDMA NIC is still working. And the other nice thing is that this does not depend on the network asynchrony. The only thing that you need to be able to do as a remote node is to access the counter. It doesn't matter how long it took to access the counter. It could have taken like 5 years. It doesn't matter. So we don't have false positives there. And so the takeaway is that really, if you can somehow manage to take network synchrony out of the equation, then you can have fast and accurate failure detection. Then the second part, when you have a nice failure detector that works at microsecond-scale, is to update the membership in a consistent manner. So to do so, uKharon uses plain old Paxos, but plays a very nice trick. So because it optimizes it for RDMA. Unfortunately, I will have to go over Paxos very briefly, not trying to explain how it works and why it works, but how it works. So in Paxos, we have two kinds of nodes. We have proposers and acceptors. The acceptors, they truly are the only one to maintain some state, and this state is pretty minimal. And for a proposer to decide, for instance, on a sequence of memberships, the only thing it does is that it's going to invoke two RPCs at the acceptors. And those RPCs, as you can see, they are dead simple. The acceptor just gets some value from the proposer. It uses this value to update its local state, and then it returns one of its local variable. Super simple. The problem with Paxos is that it involves the CPU on both sides. So the trick we're playing there is that we move all this logic there on the side of the proposer. So we take everything away from the acceptor except for the state, and we transform the original RPC into a one-sided one. How does it work? Well, very simple. First, the proposer reads the state from the acceptor locally, and it gets it local. Then it applies the transformation on the local state that it fetched, and then it uses a compare and swap to update the state of the remote acceptor. And the nice thing here is that this compare and swap ensures that this remote invocation of the RPC is absolutely equivalent to an RPC that would be running on the acceptor. And so the takeaway here is that by using one-sided RPCs, well, we're actually able to achieve blazing fast consensus. Then the next thing that you want to do once you have decided on a sequence of memberships is to make sure that there's no one living in a previous membership. So if we go back to the issue we had at the beginning of the presentation, so the client had gotten a membership, but he didn't know whether that membership was actually the active one, the current one, the one in which everyone should be operating. So what is the active membership? We expose that with a method that we call the active method, to which the client is simply going to give a membership and get back a Boolean saying yes or no, this thing is the active one. How it works, that simple. The client is just going to ask the membership service. Then, when it knows that that membership is active, and when it gets the yes, the thing is active, it knows that at some point between the invocation and the response of the method, that membership was active. So then it contacts the cache, and finally, after having read the value from the cache, it calls again active. And what it knows there is that because the membership was active before and also after reading from the cache, then that membership was active all the way through when we were reading the cache. So the read there was not pulling some stale data. The problem with this approach is that it has super high latency, as you can see. In this example, we just tripled the latency of our service. So how could we kind of preserve the semantics of this active call, but make sure that it has as low overhead as possible? And our answer is to use leases. And moreover, what we want is that those leases should be as small as possible, because the longer leases are in the distributed system, the longer it's going to take to move on to the next configuration. So if we can get leases to work at a microsecond scale, then that's great. And that's what we do. So the clients, they lease the result of the active method for 20 micros. Then they keep on renewing the leases that they have on this thing in the background to be sure that they always have some way of getting the result from active locally. So if we go back to our previous example, now the client is split in two parts, the background and the foreground. And so as I was saying, the background is going to get a lease and renew it. So that now, when the client wants to read some data from the cache, it can simply check if the membership it has is the active one locally, zero overhead, almost, read from the cache, and then it's going to sandwich again the operation, but with very low overhead, as you can see. And the great thing with that scheme is that it does not require clocks to be synchronized within the system. That is, as you can see, we never sent a timestamp over the network. We're able to have leases without communicating about what this guy thought about the time was to the membership service. The only thing that we require is that the clock drift is bounded, so that the time when measured at the client is approximately the same as the time when measured at another client. And this allows you to have, because you don't have synchronized clocks, to have leases that last approximately 20 micros. And because you are leasing, your overhead is no more than 40 nanos at the end of the day. So that was it for how uKharon briefly works. I mean, that's just a summary. Now the question is, how does it perform? So we are moving to the evaluation. So first of all, our setup. Our setup is comprised of 8 nodes. They are all linked together via 100 gigabps switch. We have 3 nodes that we are using to replicate uKharon, 2 nodes that we use for the service that we're going to benchmark uKharon through, and then we have 3 clients that we use to put load on the system. The first point we're trying to make in our evaluation was that, indeed, by using uKharon, you could build super fast, distributed, reliable services. And so we used uKharon to implement a replicated key value store. So what we did is that we took the state of the art for a key value store that is ERD, And we compared our implementation, our replication scheme, that is this one here on the right, with what you would get by replicating it with mu, mu being the fastest SMR, state machine replication system available that is tailored for RDMA. So so what we benchmarked was the latency of GET requests, of puts, and also the failover of the system. What you can see is that for GET requests, we don't have much penalty between the version that is unreplicated of herd and the one that uses Microsecond KB. The reason why is that, again, we're using the active method as described before, which has very low overhead. On the other hand, when you replicate the key value store using mu, because it's doing state machine replication, it has to replicate the GET requests. So you will have a lot of overhead, and that's what you can see here. Then, if we move to put requests, we're not getting like that much performance, and actually this is attributed to implementation details. So you can assume that both systems work at the same speed. And finally, for the failover here, we have a huge, huge difference between when replicated with mu and when replicated using Microsecond. The reason why is that for mu to be that fast, it uses RDMA permissions. And setting permissions using RDMA is a control path operation. And control path operations, they don't work at the microsecond scale. Whereas in the case of Microsecond, well, as we have seen previously, we can fail over in 50 micros, and that's what we get. And so by using Microsecond, you can be the state of the art. Then the second experiment that we have is like, do they actually work, those leases that you were describing, only lasting approximately 20 micros? Because maybe it sounds a bit too good to be true, sorry. So what we did in this experiment is that we tested our leases with different amount of network load and different amount of memory load. And so we have 4 graphs. And so the x-axis is different leases durations that we tried. And on the y-axis, what you can see is the proportion of requests, of leases that were renewed on time. And what you can see is that it doesn't matter the network load. As long as you're not like saturating the network, you will be able to get your leases renewed in time. And that's what you can see here with with the leases being super stable. So that was it for Microsecond. Let me conclude very briefly. So Microsecond is a membership service for microsecond fast failover down to 50 micros. It's super easy to integrate, really. It's just this active method that you have to call at the right time, depending on the semantics of your program. Given our implementation of this active method, we have actually very low overhead. So Microsecond went through the artifact review wall, and it got both functional and reproduced. Unfortunately, we're not able to make our GitHub public in time to get the first batch, but don't worry, because the thing is now public, so you can play with Microsecond. And it's still a prototype, but you can absolutely use it to test your applications. Of course, I couldn't go in all the details, so be sure to check out our paper for more details. And that was it for me, and I will be glad to take your questions, if any.